Sometimes when there's a lot of work to do, it's easier to grab all the work that we have to do and divide it amongst a number of people so that everybody can be working in parallel. Well, that is the principle behind multi-threading. In today's video, we're going to be reviewing the principles of multi-threading utilizing Java. What is multi-threading? Multi-threading is simply grabbing the main task and splitting it into subtasks and then having those tasks perform jobs in parallel and then have them joined to the main task so that the task can continue. The computer is going to try to fake that it can work on many things at the same time. Let's say that the entire tasks are represented by the circles down here. The computer will split its own CPU time by switching context between each one of these tasks. So the computer will start working in this fashion. It will do a little chunk of task 1, performing a chunk of task 2, a chunk of task 3. Then it will go back into task 1, task 2, task 3. And again, continue with the entire process as it can complete all the tasks to what us seem like it's at the same time. This is an oversimplification of what the computer is doing in reality, but because the operating system might prioritize so that task 1 is the one that finishes first, and then task 3 and then task 2 might complete as the CPU and the computer see fit. However, the important thing here is to remember that the computer is just splitting its own CPU time so that the task can be done at the same time. Here's a simplification of what happens internally. The computer will need resources that might be coming from a database or disk or external resource, something that might be a little bit more expensive to retrieve from time-wise. So as the computer is putting these from, say, data source into the RAM, this operation that might require some I/O or input and output from disk into memory and then from memory into the CPU might take a certain amount of time. While the computer is waiting for that information to go in from the hard drive to the RAM to the CPU, it's useful for the computer to say, well, while that task is happening, I'm going to be processing some time on task 1, and so on. As the computer is trying to read data from other sources, it's simpler, or it's better, more efficient to be running some of the tasks as the CPU sees fit. All these operations come at a cost. There's a lot, just like grabbing a stack of work. Or let's say we're all gonna fold the laundry and we distribute all the things that we have to fold. It might require certain coordination just to have everybody that it's working to be more or less organized. It happens in the same way with the computer. Just because you're adding more threads to a job doesn't necessarily mean that you're going to be cutting the work in half. There will be in half plus overhead of communication and resource sharing. That is basically the same thing that is going to happen inside of the computer. Java has been built in with multi-threading in mind. And that was one of the big improvements from the old days where in C you had to handle things pretty much by yourself. Here, Java provides 2 entry points. The easiest way is to just have your object inherit from the thread class. Knowing that might not be possible in every single situation because you cannot have multiple inheritance, Java also provides the Runnable Interface that contains all the ingredients appropriate, all the ingredients needed for you to run your program in a multi-threaded way. The thread class or the thread object is already implementing that Runnable Interface. Let's go into GitHub and go to my page /threading samples, we can clone and download that code and open it up with IntelliJ. This is a very simple threading example where I have a class that extends from thread, and what is going to happen is that we can create those threads, and when we call the .start method, Java is going to take care of setting up the threads and forking them. We're going to have our main thread, and our main thread is going to then fork and start and continue its own process. This is the main, and it's going to then fork into a new thread, which in this case we are actually forking into thread 1 and thread 2 while the main thread continues. And these tasks are going to, this is the start part, the start method, and once it starts that that new thread, the run function is called. That is why in our code the threaded code is starting here, even though that we have that start method. Start just told the virtual machine just to fork that new process, and when it's actually ready, then it's going to call this run method. In here I am doing something very simple. I'm going to count through 10 and then just finish the process. Now there is something to notice. Let's execute the code, and what we notice is that we started the process and then done was not really printed after it had run all these guys in the middle. I called thread, the first thread I called it thread 1, and the other one I called it thread 2. Why did I do that? So that way when you are printing which thread is actually printing the data, I am essentially printing the thread name and the count iteration. So you can see that thread 2 started printing first, then thread 1, then you can see that in some cases, essentially they're both doing one after the other. It's like a 1-2 punch. The most interesting thing is that done was printed before the end of those threads. And the reason is because when we do the start calls, Java is not going to wait for this thread to be done. It's just essentially going to fork it and then continue its execution. In other words, if we go back to our diagram, as it spawned the processes, and then here it's where it printed done. These two guys counted through 10 and then finished their execution. Let's say, and then these guys finished their execution, and then the main process finished its execution as well. So how do we make it so that done is printed at the very end, so that way we can't do anything until the two processes are done working in parallel. In other words, we have a boss and we have two workers. In other words, we have a boss and we have two workers that are doing the work, and then when they're done, they should, instead of just dying, which is what happened here, they should report back to the main thread, where the boss can continue the execution. So how do we achieve that? Well, if we add, after all the threads have been started, if we say that we are going to wait for that thread to finish, we can call the join function on all the existing threads. And when we do that, what it's going to do is that it's going to block the main thread. This thing is going to be waiting until these two guys are done. So if we run it now, it's going to have an error. Why is that? Because it's actually expecting an interruption to be caught around these two guys. So what I'm going to do is that I'm going to Alt Enter. I'm going to put both of these guys surrounded by a thread execution. And that is just in case that you hit Control C, you can actually try to finish whatever work, because sometimes it's needed to clean up whatever work that the threads actually did. So now that we're waiting, after we started the threads, we are waiting for these guys. The done line, which is afterwards, was printed after everything was executed from both threads. Now, what would happen if we moved, let's say we are going to play a little bit with this code. And we start the first thread and then join it, and then start the second thread and then join it. What is going to happen is that essentially we're nullifying the threading mechanism, but we are also going to be, because we are going to be running the first thread, then wait, then the second thread, then wait. So here we can see it very clear that it was uno, 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 then dos, 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 dos. If we make them both start at the same time and then wait for them together, we can then see that they essentially worked in parallel. Where sometimes, yes, there was two of the same threads working at the same time. That means that the CPU could fit in two actions of the same process in the same allocated time that it had for it. Now, the order of execution is not really guaranteed here. Why? Because the OS is going to be the one that it's going to be taking care of how much of those fractions of time it allocates. So for one thread, it might actually say, you know what, I've got enough time for these three. And then the second time that it executes, or that it goes back to that same process, it might only just do one thing. And then the next time, two. It just depends on how much work the CPU has that it can actually allocate for that particular chunk of time that it was working on. One of the biggest challenges with multi-threading is what is known as a race condition. A race condition is, in simple terms, two objects racing towards sharing the same resource. For example, we have this marble game, and here we can clearly see how both of the marbles are competing for the same space where there's only room for one of those. You can see that the marble gets kicked out of the way because a race condition in some cases worked, in some cases, obscure cases where the timing is correct, things will collide. So Java, when it was designed with this in mind. And one of the solutions around it is called a semaphore, which is a fancy word for traffic light, which essentially allows us to lock a resource and prevent something from going on in the same road. Actually, a traffic light is a perfect example. If you didn't have traffic lights or any way to stop traffic, you could potentially cause a collision whenever the timing is right for that to happen. So Java introduces the keyword synchronized, which if we go to the thread sync file in the repository, we're gonna see this code that essentially, if we maximize it, and let's go into going into presentation mode, that way we don't have any distraction, we can see that it's a thread sync that extends from thread. That's the name of the class. We have we're going to be counting to 10, but each thread is going to be trying to increment, and the count is static, means that it's going to be shared. Both the max limit and the count are going to be shared resources. So when we run 3 threads trying to run the code, if we go and click on run, we can see that right now, because this function, the one that it's called on the run, where it's trying to count for each count, it's trying to increment it in a synchronized way. That means that this function is not going to be called, it's going to be locked each time a thread tries to access it. So that way, certain write operations. Remember that we were discussing that threads were really useful for reading, processing, and writing at the same time. write operations can be synchronized, so that way there's no collision when writing two things at the same time. So if you're writing file A and file B, you can have both entries go into the same file without just one being there because the other one destroyed it. So what happens if we remove this synchronized keyword? Well, let's just remove it and rerun our code that it's going to be trying to share. So you can see that count. So you can see that the thread before it wrote the count went from 0 to 2. Both threads were going towards the same thing. Then thread 1, thread 3 went in and incremented it to 3. Then thread 1 came in and incremented it to 4. But you can see how things, for example, this one, it's like all over the place. It was not really, the reads happened a lot sooner than the writes, and it just kept, instead of incrementing, it really did it finished with a count of 5. So you can see it went from 0 to 2, 3 to 4, then 2 to 3, then 4 to 6. So it's all over the place, as opposed to if we add the keyword synchronized and we rerun the code, everything is 0, 1, 2, 3, 4, 5, 6, and here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Again, it's all based on that resource that is allowing us to increment that variable. As we are writing it back, this line is just essentially allowing us to prevent this resource collision. One extra thing that I would like to point out is how much faster things could be on a threaded project. So there are two files where we can actually do a fair comparison. What we're going to be doing in this dual example is that we are defining a class that it's called Climate Reader. What this class is doing is that it's reading reading a monthly temperature from the NOAA, which measures the global temperatures. So this code is going to try to read from 1880 to 2017. It's going to try to retrieve the URL, what the API from the NOAA reports, and then it's going to print the results from that. So it's going to do it in an increment of 10 years. So if we were going to get it in a single thread, just going from 1880, 1890, 18, etc., all those until 2017, we can see that given the time differences that we're seeing here, that this time calculation, by the time that it's done in almost 6 seconds, 5,976 milliseconds. That is on a single thread, just going essentially, if we see here, from 1880 to 1890, 1900, 1910, 1920, each decade is calling the resource, and since a lot of that is I/O, it's essentially just waiting for it to finish the first one, then the next one, then the next one, then the next one, then the next one. What happens when we do the same function? We're doing a climate reader. It's the exact same thing, but what we're doing is that we are doing it in parallel. So what we're doing is that we're creating 4 threads and just dividing the calculation from 1880 to 2017 and essentially assigning the work. So here what we're doing is that we're going to be assigning the work that each thread is going to have to do. And then it lets it go and calculate. So what we're doing is that from, say, the date ranges from 1880 to 2017 is dividing it by the number of threads and saying, okay, this first portion of from 1880 to say 1916, I think it is the first one, if I remember my math. That's the first chunk. Then the second chunk is from 1917 to I think 36 years, if I remember the math that I did when I wrote this code, and so on. So it's doing it by, like, there's 4 blocks working in smaller date ranges, but all at the same time. So the other one was 6 seconds, and we go in here and it says, yeah, almost 6 seconds. And if we run this one, which is essentially using the same climate reader code, it did it in almost 2.5 seconds. So it's a dramatic improvement, just to do the same job. Now there are certain other implications, such as in the other output we had an ordered list of when the data came in. So here we have to do some processing because the one from the 1940s, 1980s, 1914, and 1880, all of those were the first ones to return. So at some point we would have to sort all that data. It makes a lot of sense that an operation of sorting all the data is a lot faster or cheaper than having to wait for a linear return of all those values. So yes, there are certain other compensations that you need to do, and of course there's a lot more management that you need to do to first divide the work and then organize it. But in some cases it's actually worth it. In some others it might not be, depending on the amount of the data. I think that what happens is that there's a tipping point when the data, the amount of gains that you can do goes to a certain peak, and then after that the gains decline if you add more threads. So say that we added 1 thread per each entry, it would be way past the peak. So the optimum is, it's reached, the optimum amount of threads might be reached at some point, and then adding more threads subsequently decreases. I hope that this simple explanation of threading allowed you to understand the complexities of threading, and I would love to hear any comments or any extra information, what you like, what you dislike. Write it down in the comments if you can. You can hit like on this video or even subscribe to my channel, and I would love that. Okay, see you around next time. Bye bye.